The concept of a volcanic winter pertains to a worldwide temperature decline, prompted by sulfuric acid droplets that veil the sun and heighten Earth's albedo, or its reflectiveness of solar radiation, an event typically triggered by a substantial, sulfur-laden, and highly explosive volcanic eruption. The subsequent climate changes hinge heavily on the volume of sulfur dioxide, SO2, and hydrogen sulfide, hues that are propelled into the stratosphere where they interact with molecules of water, 2, and hydroxyl O to develop sulfuric acid. O to develop sulfuric acid, his process then forms 8,2-O4 aerosols, which are chiefly responsible for radiative effect. These volcanic origin aerosols function by reflecting solar radiation, which cools the surface, and absorbing terrestrial radiation, which warms the stratosphere. The cooling effect thus initiated can persist due to interplays between the atmosphere, ice, and ocean. These feedback mechanisms may uphold the cold climate even after the dissipating of volcanic aerosol. A powerful volcanic eruption discharges magma elements, including volcanic ash and gases, into the atmosphere. While majorly the volcanic ash settles to the ground locally within weeks of the eruption, the released SO2 facilitates the formation of openation of H2SO4 aerosols within the stratosphere. These aerosols are capable of reaching the opposite side of the hemisphere from the eruption site within weeks, remaining in the atmosphere for roughly a year. Their radiative influence can hence endure for numerous years. However, factors such as the eruption season, the volcano's latitude, and the altitude of the SO2 injection significantly determine the volcanic cloud's stratospheric dispersion and its climate impact. The lifetime of these aerosols is shortened if they result from extratropical eruptions as compared to tropical ones due to an extended transport path from the tropics to removal across the mid- or high-latitude tropopause. Winter injections are also radiatively less efficient than summer ones concerning high-latitude volcanic eruptions due to enhanced elimination of stratospheric aerosols in polar regions. The sulfate aerosol interacts robustly with solar radiation by propagation, resulting in conspicuous atmospheric optical phenomena in the stratosphere, such as solar dimming, bishop's rings or coronae, peculiar twilight hues, and dark total lunar eclipses. Accounts of these atmospheric occurrences dating back before the Common Era signify instances of volcanic winters. Post-eruption surface temperature observations demonstrate no correlation between the eruption size and the extent of climate cooling, revealing that the size of the eruption doesn't necessarily correlate with the volume of SO2 released. This proposal suggests that a series of large and closely grouped volcanic eruptions may have instigated or amplified various significant climate events in Earth's history, including the Little Ice Age and the Late Antique Little Ice Age. Among other such effects may have been achieved through complicated positive feedback interactions among the atmosphere, ice, and oceans. An essential aspect of this proposed theory focuses on how vast amounts of rapidly erupted volcanic material might have influenced Earth's silicate weathering cycle, a process that occurs over tens of millions of years. This cycle entails the reaction of weathered silicate minerals with carbon dioxide and water, forming magnesium carbonate and calcium carbonate, which is eventually stored at the bottom of the ocean, thus reducing atmospheric CO2 content. The eruption of a large volume of volcanic materials could amplify this process, resulting in a global temperature drop. A prominent example is the Sturtian glaciation, regarded as the most extreme and widespread glacial event in Earth's history, believed to have occurred due to the weathering of erupted material from the Franklin Large Igneous Province. Data drawn from tree rings, historical dust veil records, and ice core studies confirm that some of the coldest years over the past 5,000 years can be directly attributed to huge volcanic SO2 emissions. Similarly, hemispheric temperature anomalies resulting from volcanic eruptions have primarily been reconstructed using tree ring data for the past 2,000 years. This document provides a non-comprehensive overview of significant global cooling incidents attributed to volcanic aerosols. Frequently, the specific source volcanoes responsible are unknown. For instance, during the last glacial period, substantial volcanic coolings have been inferred based on the scale of datino irregularities. One significant volcanic event from this period is the eruption of the youngest Toba tuff, Idit, which has been the subject of intense debates regarding its potential climate effect. This eruption, occurring approximately 74,000 years ago from Toba caldera, is considered the largest known quaternary eruption The colossal size of this eruption has fueled ongoing discussions about its worldwide and regional impact on climate. The narrative focuses on the theory that the idit, or the eruption of the supervolcano Toba, may have significantly impacted environmental changes and evolutionary events. It is suggested that the YIT likely occurred during the Gs20 cooling phase, potentially exacerbating its intensity. Whilst some geographical regions, such as the South China Sea and Lake Malawi, experienced drastic episodes of extended droughts and cooling after the YIT, the exact causation relationship remains debated due to pre-existing environmental shifts. The narrative then shifts back in time to a more severe phase of global glaciation, the Sturtian glaciation, which started about 717 million years ago. This ice age is framed as the most drastic in Earth's history, with the whole planet submerged under ice for about 60 million years. This freezing spell has been linked to multiple colossal volcanic eruptions, which are believed to have rapidly cooled the global temperature by impacting the atmospheric CO2 level. These eruptions also triggered extreme weathering, further intensifying the cold spell. The narrative further suggests that such drastic environmental shifts, including volcanic winters, were key in bringing about evolutionary changes by causing population bottlenecks. Such bottlenecks lead to a significant reduction in a species' numbers, and thus speed up evolutionary differentiation as a result of decreased genetic diversity. This concept is illustrated through the Lake Toba bottleneck, which supposedly reduced human population to incredibly low level.